Welcome back to another Go video. We'll be learning concurrency in Go, which is something Go is known for. Go routines and all that stuff. People praise how Go has implemented concurrency. Many languages have concurrency or some form of multi-threading implementation. But Go's is very much praised for that. So we'll be learning Go's concurrency, which I've been very much interested in doing so. We we did mocking yesterday, but the last video, not fully, but to some extent. We'll get back to it, but I just wanted to learn concurrency because frankly it sounds more cool. So yeah, let's go. Here's the setup. A colleague has written a function check websites that checks status of a list of URLs. Okay, so we have a package concurrency and we have type website checker, which is a func that takes a string and returns a boolean. And we have a func called check website which takes in wc, which is the function which does this, which takes in a string and returns a bool. And we have a slice of urls, and then we return uh, essentially a map with the value of key, with the key being string and value being a boolean. And we say results make, okay, we essentially dynamically allocate this. And we say for range urls, so we basically this gives you the index, so it gives you the value. And so we say results url wc url. So I'm assuming website checker function will pretty much just take this url, return a boolean whether it's online or not, and then return the results. Okay, it returns a map of each URL checked to a boolean true for good response, false, bad response. You also have to pass in website checker, which takes a single URL and returns a boolean. This is used by the function check all the websites. Using dependency injection has allowed them to test the function without making real HTTP calls, making it reliable and fast. Here's the test they have written. So here we have so here what we have done is we have made func mock website checker, which pretty much matches the function prototype, and it says return URL not equal to this. So we did test website checker and we do this and we say websites. So this is the slice of websites that we have, and we want this, and we got check website, mock website checker websites, and this. The function is in production and being used to check hundreds of websites. But your colleague has started to get complaints that it's slow, so they've asked you to help. So the thing is, right, return URL, is URL not equal to this? So is Google not equal to this? True. Is Google not equal to this? True. Is this not equal to this? Well, false. Right, the function is in production and being used to check hundreds of websites, but your colleague has started to get complaints that it's slow, so they have asked you to help speed up. um let's put this under concurrency, right? Let's put this under concurrency. And what should I name this? I should name this um what should I name this? Let's check. I'm very bad with namings. I'm really bad with namings. Trust me, I'm very bad. Seems like it's check websites.co. uh let's just call it check websites.co. And we do this obviously, or this actually, right? We call in the, first of all we do that, and then we call the benchmark testing obviously, right? So we get this. So if I do check website, if I something like package concurrency, and I say type website check, I actually even just paste the code because there's nothing intellectually interesting over here. um, right, okay, so essentially this is what's happening. And then we check this, so we write a simple test is over here. right? So essentially, yeah. So we want this map. Okay, let's run this. Let's go into cd concurrency and let's go run test. Go test. Sorry, it passed. Great. So now someone says, well, it's kind of slow, right? Let's write a benchmark to test the speed of check website so we can see the effect of our changes. So we say, okay, so we have this func, which, okay, I think what this is trying to say is it takes in a string but doesn't really use it, and we return a bool, say time for sleep 20 into time, so 20 milliseconds you sleep and return true. So we say func benchmark check websites this, and we say URLs. We make around, I'm assuming this means 100. Um, or is it like, or is it slice? Um, okay, even I thought that. And so for that we say a URL, and we say for b dot loop check website slow website checker. Why are we making it slow though? Okay, so we do import to slow website checker because this is our URL. Okay, and then we say something like go test. Wow. Now we can finally talk about concurrency, which for the purpose of the following means having more than one thing in progress. Having more than one thing in progress. So I think one thing that I think people get confused a lot between concurrency and parallelism, right? Imagine you have a single core, and you like, what is a core? Just think about core as a single unit of electronics, or like a single component that can perform tasks. Okay, it can perform calculation and stuff, right? It's like a CPU. It can do stuff. And let's say you have multiple tasks, like this is task one, this is task two, and this is task three. Now you have a single core. Let's say your CPU has been assigned to do task one, right? Now you're doing something in task one, and let's say task one requires IO operation. So when it requires IO operation, it's using DMA, right, or some other form of IO interface. That time the CPU is not used. So while this is using IO, your CPU is just idle. While the idea is, instead of making your CPU just keeping it serialized, we could, instead of waiting for the CPU to finish its IO operation, while it's doing its IO operation, the CPU can be provisioned to another task and it can continue that task. Let's say it does that task to some value, and then this task says, okay, I'm done with my file IO. The CPU stops this, and obviously put of pretty much all of the context, it saves it somewhere, and then it context switches to where this has stopped and comes back to the CPU, right? And this is like concurrency. You're doing more than one things. Parallelism is when you have multiple cores, and those multiple, so imagine you have like multiple cores. Okay, you have multiple CPU cores. Like you have in your laptop, I think you have more than I don't worry about it. So and now you could do things in parallel at the same time. Over here, what was happening is it's still happening sequentially, right? T1 stops over here, right? It goes, then you do T2. While over here you can do T1 and T2 at the same time. That is your parallelism, right? So It's having that okay, so having more than one thing in progress, that is the right thing to say. So over here, what we are doing, as you can see, if you run this, um, you see I have around, how many cores do I have? But I had 3.10 gigabytes, that's not bad. Anyhow, so as you can see, this does it sequentially, it just goes through it sequentially and does it. For instance, this morning I made a cup of tea, I put the kettle on, and then while I was waiting for it to boil, as you can see, this could be thought of as an IO operation, right? It's something that does not require your attention because it's going to do it by yourself. If you can understand why it's faster to make tea the first way, then you can understand how we will make check websites faster. Instead of waiting for a website to respond before sending a request to the next website, we'll tell a computer to make the next request while it is waiting. Normally in Go, when we call a function do something, we wait for it to return. Even if it has no value to return, we will wait for finish. We say that the operation is blocking. It makes us wait for it to finish. An operation that does not block in Go will run in a separate process called goroutine. So let's read through this. Normally in Go, when we call a function do something, we wait for it to return. Even if it has no value to return, we'll wait for it to finish. We say that this operation is blocking. It means it makes us to wait for it to finish. An operation that does not block in Go will run in a separate process called goroutine. Think of a process as reading down the page of a Go code from top to bottom, going inside each function where it gets called to read what it does. When a separate process starts, it's like another reader begins reading inside the function, leaving the original reader to carry on going down the page. That's well explained. To tell Go to start a new Go routine, we turn a function call into a Go statement by putting the keyword Go in front of it. So to say Go that this can be done, okay, so I think I understood what's happening. Normal functions are blocking, but a Go function will run in a separate process. We turn the function call into a Go statement by putting the keyword Go in front of do something. Um, so as you see, we have func check website, and it's very funny enough. What we say over here is we now say we say go, and we call this is anonymous func, and we say results URL equal to World Cup URL. Um, so I think there's something wrong. Okay, so yeah, we do a anonymous function call. This is how we do it, and so we initialize a go routine over here, which essentially runs this function. And I think the idea over here is that this now, the way it has been done, this will run in a separate thread, so we can like parallelize it. Anonymous functions have a number of features which makes them useful, two of which we are using above. Firstly, they can be executed at the same time declared. This is what the okay, so we are declaring the anonymous function and then we are actually running it with these two brackets mean signify. Anonymous functions have a number of features which make them useful, two of which at the end of the anonymous functions, at the end of the anonymous function is doing. Secondly, they maintain access to the lexical scope in which they define all the variables that they're available at the point when you declare the anonymous functions are also available in the function in the body of the function. The body of the anonymous function above is just the same as the loop before. The loop body was before. The only difference is each iteration of the loop will start a new coroutine concurrent with the current process. So it creates, so essentially at every loop, it creates a coroutine. Interesting. Yeah, this is pretty much the reader-writer effect. The reader-writer issue that we read. So this is data race, a bug that occurs when two or more coroutines access the same memory location concurrently, and at least one of these access the reader-writer. Yeah, of course. Go can help us spot these conditions with its inbuilt race detector. I wonder how it works. I wonder how it works. When you hold this feature on. Hmm, interesting. So essentially, what the author is saying, we can say time dot time dot sleep. That should be enough. Right? If we on go test now, so it pretty much waits for all of them. I guess what's happening is at each iteration it runs a coroutine. So coroutine spawns a coroutine, and then we're just pretty much returning it. So it's not we're not giving enough time for all the coroutines to actually do something. So that's the issue. Why? Um, what does the benchmark does exactly? Benchmark actually just sleeps. No, it still worked, but I don't know. Go test race. Um, yeah, that's crazy. Yeah, so this is being called over here at website checker. Okay, we can solve this data race by coordinating our routines using channels. Channels are a core data structure that can both receive and send values. These operations, along with the details, allow communication between different processes. In this case, you want to think about a communication between the parent process and each of its coroutines that it makes to do the work of running of such a function with the URL. Okay, so in this case, when we think about communications between, so channels essentially are data structures that allow to send and receive values between different processes. I think if I assume it as a different process, much better. So yeah. Okay, so let's think about this. So we have type this. Okay, we have a type thing. We have a result which contains a string and bool without any value associated with it. Um, okay, what's happening? So we have result channel which seems to make some form of keyword result, and we say result channel result URL WC URL. Hmm. Okay, what's happening over here? I'm getting so confused. Um, what do I think about Go code? I don't know. Sometimes I look at Go code and start like, मैं क्या कर रहा हूँ मैं life के साथ. Okay, let's see what's happening over here. So we make a struct without actually doing something to it, which is weird. Um, we have results, which is make of this. We have result channel, which is make of God knows what chan means. And then we run this and we say result channel results. Okay, and then we iterate through the length of the URLs. R. Okay, what's happening? Okay, this is channel. The new type result has been made to associate with return value website checker. Uh, um, a new type has been made to associate the return value of website checker. Website checker का return value bool है. We are sending a result struct for each call to. This uses the next for loop. Okay. Next, we iterate over the URL. Instead of writing to the map directly, we are sending a result struct for each call. Next for loop iterates once for each of the URLs inside. Instead we are using a receiving expression which assigns a value received from a channel to a variable. This also uses the what is happening. We have used concurrency for part of code. Often misattributed to can mark is make it work, make it right, pass. Make it work. Make it work. So why make where work is making the test pass. Okay, right is refactoring the code. Okay, and fast is optimizing the code. Yeah, that's premature optimization. Yeah. So first of all, we make it work. We make it right. So we do any refactoring and then we make it fast. Okay, I think I might have to watch few videos on this. Go routines, concurrency in Go YouTube video. Go routines explain. I want to like learn it properly. Um, it was like a watch. Like let's just go through this video.
In the first video, Learn Go in 12 minutes, we had a very quick look at the main features of the language, so you could get going straight away. One thing I didn't talk about though was the support for concurrency that
Let's go through this. I guess learn Go in 12 minutes. I can put it in my resume. Let's go.
Go is a really popular language at the moment, and for good reason. It's a really great language to learn. I'm going to give you an overview of the language, and by the end of the video, you'll hopefully have the skills that you need to write simple Go programs. If you go to golang.org, you'll find a link to the
Okay, sorry. Let's
download
sorry.
and install Go. If you're on a Mac, you can use brew install Go if you find that easier. Once you've done that, you'll have the Go command line tools available. When it comes to creating a Go project, you might find it a little different to what you're used to in other languages. The idea in Go is that all of your projects live in the same place, and this place is called your workspace. By default, this is a folder called Go in your home directory, and you can see this if you type go env go path. So I'm going to actually create this folder. This is our workspace. Inside here we need another folder called src, and this is where all of our source code is going to go. So now inside of src you can create a folder for each of your projects. Let's make our first Go file. You'll often see them being called main.go, but it can actually be called anything. The first line in a Go file needs to be the name of the package. Every project, at least if you want to be able to execute it, needs to have a package called main. The next section is the imports. This is where you can import different packages. There are loads of useful packages in the standard library. A common one is FMT, which has functions related to input and output. So open brackets, and then you can list out all of the packages that you want to import. Note there are no commas in this list. We'll just use FMT for now. Next, let's look at functions. You use the func keyword followed by the name of the function, and the first one you'll want is a function called main. It takes no arguments and it doesn't return anything. But this is where the program starts, a function called main inside of the package called main. This will output hello world to the terminal. To run this, you can use go run followed by the name of the file. If you want to compile the code into an executable, then you can use go build in the program's directory. So this time it doesn't run our code, there's no output here in the terminal, but what it has created is this binary file here. This is an executable. In Windows, it's going to be a .exe file, and we can run that in the terminal. Alternatively, you can use go install. This is going to do something very similar, except the executable is put in this bin folder. It sits in our workspace next to the source folder, and if this program had external dependencies, so if we'd imported something from outside of the standard library, it would compile and cache those dependencies into a package folder. Let's go back to our Go file and look at variables. To declare a variable, you use the var keyword followed by the name of the variable and then the type. So I'll make an int, I can output this. If we don't provide an initial value, then the zero value for the type will be used. Every type has a zero value. For integers, the zero value is literally just zero. For strings, for example, the zero value is the empty string. I could later assign something to this variable, or I could do it at the same time as declaring it. So I could do this again, and then add the two integers together. So we get 12. When we give variables an initial value like we're doing here, there's a shorthand syntax that we can use. Drop the var, add a colon and an equals, and then the value. And we can omit the type.
I don't like that. That takes it away the type, and also like one common thing you'll see in bunch of this is let's just take some example of like go code over here. Yeah, so if I say something like let's say I wanna make var x float 32, and I really wanna use some float 34, and this is like something I need. And let's say I do fmt dot printf, and if I do hello world go run hello.go, you see. But the thing is, right, and if you see this, the thing is, right, if I now, instead of doing this, if I instead say x equal 32 point whatever, you see now Go doesn't really know what your intention is, right? So Go will say, well, this is for 64, which I guess that's kind of like a dumb example because people would actually use it. Also, just more clearer, I would say.
Prefer it. So this is the same as what we did before. If I do this to all of them, you can see we get the same result, but this is a bit neater to read. Go has if statements. They allow you to execute a block of code if a condition is true. Note that there are no
Brackets for some reason.
There's also else if and else. Let's look at arrays. An array holds multiple elements of the same type, but the number of elements that an array holds is fixed. It has a specific length. For example, we could create an array that holds 5 ints. If we output this, we can see that it does hold 5 ints. All of the elements will be initialized with their type's 0 value. Again, in the case of ints, this is the number 0. We can use square brackets to index the array, so we could set element to position 2 to be 7.
Yeah, man.
Arrays are 0 indexed, so the first element is
It's 0.
If you want to be able to initialize the contents of an array more easily, we can use the shorthand syntax again. So drop the var, use a colon and an equals, and at the end of the line, open curly brackets, and then you can list out your values here. Now you might be thinking, arrays with a fixed length sound inconvenient.
Yeah.
Well, they are. If I wanted to add a 6th element to this array, I can't, because the length of the array is part of the array's type. To overcome this, you can use slices. Slices are an abstraction over the top of arrays to make them easier to work with.
So it's pretty much like dynamic arrays, and the way dynamic arrays work is quite funny. It's quite fun. It's pretty much an array, and obviously the actual implementation varies from code to code. But essentially, just imagine you have this is an array, and this array has some fixed size. So you'd see that whenever you do something as slice, you have two types or two variables attached to this. You have a length variable, then you have a capacity variable. Capacity variable pretty much is how many blocks are empty before this needs to be like made bigger. So let's say you have a slice of like length 4, 2, 3, 4, and capacity 4. Now, I mean, capacity right now is 0 and length is 4. So now as length is equal to our capacity, if we try to append something in this, it can't. So what it does is it creates a new array, and in most programming languages they twice the capacity plus 1. I think that's what Java does it. for their implementation of it, if I'm correct, for their string buffer implementation, and they just copy paste all of the previous value and they just put your new value. And you would say, well, this is kind of slow because this is like O of end operation, right? Because you have to, basically copy paste all of them and then do it. Yes, you're right. This is an O of n operation. But due to the fact that we are doubling our size every time it gets bigger, the amount of time we have to actually do O of this operation is very sparse, right? And so it averages out to be O of 1. That's how my teacher explained it to me, right? So that's pretty much how I think
Name maps
slices are.
don't have a fixed number of elements. So if we wanted to create a slice of ints instead of an array of ints, we simply remove the element types and leave an empty set of square brackets. So now this is a slice of ints. So why is this useful?
Let's just see the default capacity of slice in Go. Let's see what the default slice is. A new slice capacity is equal to length. We don't explain define it. Yeah, so over here length is this and this is that.
Now we can use the built-in append function to add something new to the end of the slice. Append doesn't modify the original slice, it returns a new one. Slices are backed by arrays, so here Go will be creating a new array in the background and copying stuff across, but when you use slices, you don't have to worry about it. It all happens behind the scenes. Maps are really useful. They hold key value pairs. They're
Hash
like
map.
dictionaries in Python or associative arrays in PHP. The type definition for a map is the word map, and in square brackets, the type of the keys, followed by the type of the values in the map. And to create a map, you use the built-in make function and give it this type. We can set key value pairs using square brackets. It's similar to indexing arrays. You can use the same syntax to get the value for a particular key. And you can use the delete function to remove something from the map. So square is now gone. Next, loops. The only type of loop in Go is the for loop. We declare and initialize a variable using the shorthand syntax we saw a couple of minutes ago. This is the counter. Then we set the stopping condition, so loop while I is less than 5, for example. And then after another semicolon, you can increment the counter or decrement it or do whatever you want at the end of each iteration. So this is going to go through the loop 5 times and print out the number, the value of I in each iteration.
Apparently, Go doesn't have while loop and all that. This
So
just has only
0
one
and it goes up to 4.
idea of
As soon
loop.
as it
That's
gets to
for
5,
loop,
it's not
which let's just say it's
anymore, so it stops
biased.
iterating. The for loop also doubles as a while loop, so if you delete the variable declaration from the beginning and the increment at the end, you've got a while loop. This will do the same as before. Another thing you can do with the loop is iterate over each element in an array or a slice by using range.
So I think what he's gonna do is somewhat like this. He's gonna, because it works over a slice. I think it does work over a map as well. But yeah, what he's gonna do is something like for I think so idx valve range of array, something like that. Yeah, I think that's what's gonna happen.
We get the index and it'll output.
Yeah, that's pretty much it. Yeah, that makes sense. So yeah, you could do something like, let's say, names. Why is it so laggy? I don't get it. Like, am I running like some crisis or something? Um, and we just say for. So if you don't want to like worry about the index, but you can do that. For name, you can say, or you just want to have the name. That's it. But sure, why not? Names, range names. Why is it lagging as hell, bro? fmt.printf idx is this, and name is equal to this, and then you can say idx name. Also, this should be name. My check, my bad. And yeah, if you run this, you will see. Yeah, so that's pretty much it. I think you can just run it as it. Idx plus. Can you do that? I think you can do that. Yeah. Oh well, that works.
You can do the same thing with a map, but you'll get the key instead of the index.
Yeah, pretty much. Yeah.
So far we've had everything in the main function, but we could easily create a new function. If you want to accept arguments, you just need to give them a name and a type. And if you want to return value, then you need to give the type of that after the brackets. So this is going to take 2 ints and return a different int. So we could do something really simple like this, and then call it up here.
Go is a very interesting language. I kind of like it.
Multiple return values. So if I made a square root function, which takes a float 64, it can return another float 64, and it can also return an error. These are all built-in types. Since the square roots of negative numbers are complex numbers, we can limit this function to positive inputs, only returning an error if x is less than 0. So we want to return 2 values. The first one is the float 64. We're not doing the calculation, so I'll just return 0. And then we can use the new function in the errors package, if I import that,
I think errors.new.
to create an error. Otherwise, we can do the square root. There's actually a square root function in the
Maths
so
package.
I'll just defer to that. We still need to return 2 values though.
So nil.
In this situation, we don't want to return an error, so I'll just return nil instead of an error. So now when we call our square root function, we get 2 values.
That's actually very common, the way to do that, right? It's actually very common. Yeah.
And we get an error. If the error is not nil, then that means something went wrong. So let's just output that. Otherwise, output the result. So it does the square root of a positive number. If we were to make this negative, then it's going to return an error, and we'll get this line executing instead. So that's how functions with multiple return.
I kind of like the way Go takes care of errors. I mean, I think one of those things we were able to do a bit of error thing. I think was it pointers? I'm not sure. It was either in mocking or dependency injection. I think so. We were able to do a lot of. I think it was in maps. Yep. You see, we did a bunch of error thing, and we just returned that error. Error word does not exist, and this was a dictionary error. I mean, yeah, these are just better way of doing it, but yeah, I had fun writing errors, to be honest. Like, that was fun.
And values work, it's really useful to be able to return errors like this because Go doesn't have exceptions if you're used to working with those in other languages. A struct is a collection of fields, so you can group things together
Yeah,
to
it's
create a more logical type.
pretty much like C.
Struct type. You want to do this outside of a function. Use the word type followed by the name, so this can be anything you want, and then the word struct. Inside curly brackets, you can list out the fields that you want the struct to have. Each field needs to have a name and a type. So I'm going to make this one a string, and I'm going to make this one.
The only thing that hurts my is not a semicolon at the end.
So that's the type. To create a struct of that type, you want to use the name of it, and then just like when you initialize an array or a slice, you can use curly brackets to set the fields. So first I'd set the field called name, I use a colon, and then the value. If I output this, you will see it's created a struct.
Interesting. Can I do something like... Why is it lagging? It's really hurting me, chat. Why is it lagging? Can I reload this? Why is it lagging? Is it like that? Oh, my co-FMT is gonna murder me. What's the issue? Ah, acha, acha, acha.
a specific field out of the struct, then you can use dot notation to do that. So this time
Yes.
we've just output 23. The last thing I want to talk about is pointers. If I have a variable, as we've seen, it's really easy to output that.
I wonder what will happen if I do that. Um, okay, so it doesn't really point to the memory address. Interesting. How would you do that? You can say var pp1. You can say person is equal to, and this will actually point, I think, to the same thing. Yeah, and if I were to, let's say, just dereference this, and I can say age. Yeah, you don't have to do that stuff. You can pretty much just dereference it directly as if this was just dealing with that, and say name. I wonder it has like pointer to pointer ppp1. I wonder if this is possible. And what we can do over here is pp1 dot pp1. I don't know how that will work. Um, you don't want to do this. You want to do max to max two pointers. Other than that, you don't want to take the risk. I wonder how would you do that. Is it like pp1? Ah, yeah. So you dereference that. So I think what you want to do is pp1. So you pretty much dereference that, and then you say name. Yeah, you would. All those months of grinding C finally paying out. Yeah. Okay.
But we can also get the memory address of the variable by using an ampersand.
Ampersand. It's pretty much C. Yeah.
So this gives us a pointer to I. Now if I had a function which incremented a variable, and we called it like this, this is going to be useless and not actually do anything because I is copied by value, so the increment function
Yeah.
has a copy of I. It increments that, but then since we're not returning anything, that copy is just discarded and the original variable is not modified. If, however, we pass a pointer to the variable, then the function is going to be able to look at the value at that memory reference and modify the original version. So we can accept a pointer by prefixing the type with an asterisk. We can send the pointer by using ampersand.
So pass by
What we
reference or
also do
pass
when
by
we
value.
use dereference the pointer, so we use another asterisk here. Without that, this is going to be incrementing the memory address.
And Go is smart enough to just dereference it for
Since
you.
we want to see what's at that memory address, using the asterisk, dereference it, and then increment that value. So now this actually does modify the original.
Do you really need to do that? Okay. Yeah, I mean,
I variable. Very quick introduction to pointers. I've glossed over a lot of details here. If you're unfamiliar with pointers, it's definitely worth taking the time
yeah.
to read up on them properly. But I hope.
So I think this is a great time to just switch to concurrency and Go.
Go has. This is a really big part of Go. It's a big selling point and a reason why a lot of people choose the language. So I thought.
Okay, so why is Go's approach to concurrency praised? I'm not assuming it's praised by the general public. Um, Go's concurrency approach is praised because heavily. Yeah, so essentially what this means, tag space, is you remember when I mentioned how your CPU would be executing something and then it stops it and then it does something else. And while it's doing something else, this thing gets ready and then it has to go there. So how that go there happens is something you will learn in operating system. If you ever do computer science, is something called context switching, and essentially it stores the values of the registers of pretty much every context that thing had in that thread into some memory, and that memory is sometimes called stack space. So then it takes it from the stack, and it's somewhat like subroutine nesting, to be honest. So that's how it works. This learns. Um, oh wow, it has its own runtime scheduler. Normally you have something called, normally your CPU comes up with its own process scheduler, which is somewhat like this, but it has its own scheduler channels over. Instead of forcing developers to use complex error-prone locks to share memory between threads, Go uses channels to let coroutines communicate securely by passing data back and forth. Yeah, I mean that is a huge thing, right? You will learn this in operating system where how we have to deal with concurrency is great, but it brings so many issues with it. And the first and the main one of them is race conditions, where pretty much two threads are racing towards a shared variable, and if either one's access them in a way that the other one didn't had to, if someone had to access something before this one had, it would lead to unpredictable result, which we like to call in a very fancy word non-deterministic, which you don't like at all. Concurrency is not an afterthought. The go What are the pros and cons? What are the pros and cons of Go's concurrency? Wow, automatically detect deadlock. So I'm assuming they have some kind of deadlock avoidance algorithm working in the background. Yeah. Oh, this guy. Man, he's the creator of Craft Your Own Interpreter. Yeah, I'm not gonna read this chat. I'm here because I just wanted to have just to see what the public thinks about this, and then I wanted to learn this. I'm not gonna waste my time in mediocrity.
Deserves its own
I mean, not in
video.
a sense I'm trying to say that they're mediocre. I'm trying to say that spend your time learning things rather than just seeing what other people have to say from your own opinions.
It's worth understanding that concurrency is not quite the same as parallelism. To run things in parallel means to run two things at exactly the same time. This is what happens on a multi-core processor. You have one core doing one thing and another core doing a different thing, both simultaneously. Typically though, the lines of code that make up a program have to run in the right order, which makes it hard to parallelize it and execute two lines at the same time. So concurrency is about breaking up a program into independently executing tasks that could potentially run at the same time and still getting the right result at the end. So a concurrent program is one that can be parallelized. We're not going to concern ourselves with what is happening at the CPU level and whether something is running on multiple cores or not. The Go runtime and the operating system will take care of it for us.
Yeah, I just want to ask this question because this comes in my mind. I am learning Go routines, and I just want to know that is Go routines parallelism if I'm running on a multi-core system, or is it about concurrency? Because those two things mean two different things altogether, right? So what does Go routine represent at that level? So take your time. I'll open up Claude real quick. I'll just open it. Exactly. This is Do not communicate by sharing memory. Instead, share memory by communicating. Share memory. What? Do not communicate by sharing memory. Share memory by communicating. I don't know what that meant, buddy. Anyhow, it's just
We can
because it
concentrate
depends
now
on the hardware, but think of
on the structure of our program and using the tools that Go gives us to make our code concurrent. So I've got a text editor. I'm gonna write a really
I'm gonna start doing this as well. Let me just push this a little bit. Let's keep this as package. What am I doing? Let's keep this as package main. Let's keep func main fmt dot print line hello world one. क्या बड़ी थी आप concurrency hero. I don't know, man. Go is sometimes a little bit. Anyhow, अरे यार, hell with this. I could do something like this. Func main. Should be added. Okay. What am I doing wrong? What is this package thing, bro? What is this package? I get it, but how do I do that then? Bro, I'm genuine. Genuinely scared. पढ़ना पड़ेगा भाई, पढ़ना पड़ेगा. I'll just use an online editor. This is so shit. Uh, yeah, this is much better. Cascading code. Enable win mode. Wow. Okay, guys. Right, so now this is much better. So we have this. Cool, cool. Yeah, this is much better, chat. Sorry, I just had to run
a
this.
simple function called count.
Okay.
It's gonna take a string as an argument in an infinite for loop that starts at 1 and just loops forever, counting up. I'm gonna output the number that we're at and the string that we passed in. and then I'm just going to sleep for half a second.
Can you say for I go FMTs are just like I don't know why they do that. Actually, don't really need that. I and the thing, and then we can say yeah time. Is it time? At how many like what time dot error undefined. What do you do? Time. Really, guys, I'm wasting my time. I know that. Give me a moment. What do you mean?
And I can count sheep, and then I'll make a call to count fish afterwards. So this is a synchronous
The
program.
thing about this is this like a blocking operation. So the thing about blocking operation is it will block our execution until this stops essentially.
No concurrency here. It's going to execute the count function, and it's going to wait for it to finish before moving on to the next line. But the count function never finishes, so it's just going to count sheep forever and never get to the fish.
Essentially, yeah.
Or never get.
I wonder how it is that. Uh, let's go with that. If I run this, it says what's the issues? It says undefined time dot seconds. It's undefined. In Goland, Goland. What am I saying? Okay. Wow, that's crazy. Yeah, so now if I say something like count sheep and if we remove this, run this, I don't think this they were allowed to run this, but I think I crashed it. Yep, yeah, I crashed it. Yep, I think this thing is crashed. Yeah. This thing is okay.
Get to the fish.
I'm so sorry. Yeah.
So I'll just do that until I kill it. If, however, we call the function with the word go in front of it, it won't wait for it to finish before moving on to the next line. It'll say, go and run this function in the background, and then continue to the next line immediately. And this creates what is called a go routine, and that go routine will run concurrently. So we now actually have two go routines. The main function with the main execution path of the program is a go routine, and now this new one that we've created explicitly. So these will both actually have two go routines. The main function with the main execution path of the program is a go routine, and now this new one that we've created explicitly. So these will both run side by side, and we see now it counts fish and it counts sheep.
Implicitly.
Go routines are very efficient. It's okay to make tens, hundreds, even thousands of go routines, but bear in mind that you can't make a program infinitely fast by adding more and more concurrent go routines, because ultimately you are constrained by how many cores that your CPU has. I'm going to make one tiny change to this program and run both count functions as go routines. Now you might expect this to do exactly the same as before, and you'd be almost right, but we get a very different result. We don't get anything. So what has happened? Well, in Go, when the main Go routine finishes, the program exits, regardless of what any other Go routines might be doing. Previously, the main Go routine never finished because it would have this infinite for loop in it. But now we've pushed that loop into its own Go routine, so the main function will continue immediately to the next line. But there are no more lines of code, so it's done and the program terminates. And the Go routines that we've created ourselves haven't had time to do anything. If we were to sleep for 2 seconds here, you'll see it now outputs for 2 seconds and then it terminates. You'll often see people add a call to fmt.scanline at the end of the main function to fix this problem. And this will stop the main function from immediately terminating because it'll wait. This is a blocking call. It'll wait for user input. So this gives our Go routines time to execute, and it's going to keep doing this until I press enter. And at that point, it'll move on and the main function will finish and the program will exit again. In reality though, this is not a very useful solution because it does require manual user input. What we can do instead is use a wait group. I'm going to import the sync package from the standard library.
Because we have the same issue in Java, and in Java they have something called join. So it essentially says the main thread will wait to complete its execution, and the main thread will stop its execution and wait until it is joined by these threads, and then will continue its execution to prevent this problem from arising.
Now let's just alter our program so we have one call to count, and let's just count up to 5. To use a wait group, I'm first going to create one. And it's nothing scary, it's just a counter. And I'm going to increment it by 1 to say that I have one Go routine to wait for. And it doesn't do any magic here, it's up to me to increment it. The next step is to decrement the counter when the Go routine finishes. So after this for loop, I want to decrement the counter. Now I could pass a pointer to the wait group, to the count function, but I don't think it's really the responsibility of count to deal with this. So instead, I'm going to wrap the call to count in an anonymous function. This syntax creates a function and then immediately invokes it. So this will still run as a Go routine, and inside here, I'm going to call count again. And then afterwards, I'm going to call wg.done. Since we've created this function inline, we have access to that wg variable, which is convenient, and done literally just decrements the counter by 1. So all we have so far is a counter of how many Go routines are running. The useful bit now is to call wait at the end of the main function. This will block until the counter is 0, so if any Go routines haven't finished, it'll wait. So now it's going to count to 5, count will return, we'll call done, which will decrement the counter, and then this wait will be like, oh, the counter's at 0, and allow the code to continue, and the program terminates. Really easy to use. So that's how to create a Go routine. Really simple, but not massively useful so far. What we need next are channels. A channel is a way for Go routines to communicate with each other. So far, the count function has just been outputting directly to the terminal, but what if we wanted to communicate back to the main Go routine? Well, we can accept a channel as an argument, and it's like a pipe through which you can send a message or receive a message. Channels have a type as well, so this one will be a string channel and will only be able to pass messages that are strings. Any type works though. You can even send channels through channels. So instead of outputting thing to the terminal, I'm going to use this arrow syntax to send the value of thing over the channel. So an arrow sends channels through channels. So instead of outputting thing to the terminal.
Oh, VS Code is now. Oh my god, VS Code is closed. I just want to look at the code that we did for that. Um, yeah. So what we did for here was, it's essentially just, okay. So essentially just put this into the channel. So it puts this into the channel, which is a struct of this. Oh, I could say something. Oh, it's anonymous.
I'm going to use this arrow syntax to send the value of thing
Okay.
over the channel. So an arrow pointing into the channel name will send a message. Going to get rid of the wait group stuff now. So nice simple concurrent call to count. And now we need to pass the channel in, so first we can make one using the make function.
This syntax is so like weird. What is this? We're using this everywhere, so over here also we say like C chan string.
Pass that to count, and then we can use an arrow coming out of the channel name to receive a message.
So okay, so now result channel से बाहर निकल रहा है. Okay.
Channel. So this is going to receive one message, output sheep once, and then terminate. And it's important to understand that sending and receiving are blocking operations. When you try to receive something, you have to wait for there to be a value there to receive. Similarly, when you're sending a message, it'll wait until a receiver is ready to receive. So we can see it does what we expect, it outputs sheep, and this blocking nature of channels allows us to use them to synchronize goroutines. Imagine you have two independent goroutines. Each line here is a line of code. We don't really care what it is, except down here we receive on a channel, and over in this goroutine we send on the channel. When they both execute, sometimes one will stop and start and the other will stop and start. They might be executing different code. They won't stay synchronized at all. But when this goroutine on the left tries to receive on the channel, it'll stop and wait until something is sent. And at some point, the other goroutine will reach the line where it tries to send, and then they'll be able to communicate through this channel. So at this precise moment, they're both at this communication point. So we're communicating and we're synchronizing, which is an important concept. Back to the code. This just receives one message. If we wanted to receive all of them, then we could wrap this in a for loop. So this is what we expect, but then it gets a fatal error. We get deadlock. This is because the count function is finished, but the main function is still waiting to receive on the channel, but nothing else is ever going to send a message on the channel.
Yeah, Chad, I'm gonna save this for now. I'm just getting a bit tired, to be honest. And I think we'll learn a bit of C before ending this. I have a C video. I just want to see, and because I want to code in C also a little bit, so we'll go through that. Let me set the environment up. We are back, and this was the video I wanted to learn. I love this creator. I love this guy, and I love C. So I just wanted to. And this guy he's like enthusiastic. We need more programmers like him. People who are enthusiastic about their craft. So yeah, last time we were learning about function pointers, which was hell of a fun to do. We learned how we can implement bubble sort for any generic, so to speak. So we really don't need to know what type of data it's holding in an array. We can just have the user provide this to us, and we can have a very generic bubble sort implementation. That was fun to implement, right? As you can see, that was the implementation we did in the last video. So let's call this the function pointer C. Right, so that we're proud of. So as you can see, let's see. So some type defs. So we have a func over here which takes in a void star and gives out an int as a func. So see over here, like this pretty much is applying to that. And if you see over here, if we were to, this is a square int takes in. See over here, we have array apply. And yeah, these things are cool. Let's go to main.c and yeah, just clear this up and start afresh. Why do I have Python code over here? I think this is most likely a lead code question I was doing. So we'll get rid of that, and we'll start with writing some C code. Let's write return 0, and I think I have to open WSL because for some reason GCC is not working on my PowerShell, which is sad. Um, let's call make main, and we say we run main. Why is that? Networks chat. Okay, cool. Let's go through this video. Hopefully I don't fall asleep. I'm very sleepy right now. So
the 8 bytes that make up this pointer. Well, as it turns out, you can. So what we're going to do next is cast our struct into a byte buffer and actually individually access the bytes that make up this memory so that you can really see that everything is just an array of bytes underneath it. I want to share today a realization that when I had it, it genuinely changed the way that I look at programming and approach programming problems. And if you're already an experienced programmer, you might look at this stuff and say, oh, well, obviously. But I find especially but when I did not have much low level experience and when I was coming from a high level programming language where all of this stuff is hidden from you, you never really come across it. And so once this clicks for you, you'll understand how file types are represented on the disk and how a .png image can suddenly become a little box in your image viewer, and also all the way from how network packets are transmit over the network and received and how everything is decoded, how programming languages represent different data types. To make sure that I prove to you that this is not just a random thing I'm making up, this is a technique that the Linux kernel actually uses right here in the IP packet parsing. Now, the thing that I want to get across to you is that everything is literally just bytes in the computer's memory. It's all bytes. No matter what kind of fancy abstractions we pile on top of it, it's all at the end of the day comes down to bytes. And so while like these different data types, they seem very discrete from each other. Like, think about this. How do you think that this struct is represented in the computer's memory? Now imagine if I was in a job interview with you and I asked you to give me the size of the struct in bytes. How much memory in bytes does that struct take up? You might be tempted to simply sum the size of the individual elements of that struct. And in the naive view, that is actually correct. But what's going to happen when we run this program? We're going to find something a little bit interesting. Now the size of our struct in memory here, as you can see, is 32. But if you take the sum of these elements, which actually turns out to be 20, if you sum the individual elements in that struct, we get a size of 20 bytes. Yet if we use the size of operator, it comes out to 32. Why is this? This is the naive view of how our struct would be represented in memory. So it's everything is just getting its own space that is the size of its data type. So if you take the size of a float, we say it's 4, so our first float is 4. Our characters are 6 bytes, so we've got 6. Our integer is 1 byte, so 1. U into 8 is 1. The pointer on a 64-bit system is 8. And then the boolean is 1. And so this is what in the computer's memory we would expect it to be. Why is this not the case, and where does the extra 12 come from? Well, it comes down to memory padding and memory alignment. And what you'll notice is that if you actually hover over...
This is a thing where I just I came across padding and alignment when I was implementing my own arena allocator in C for pretty much making memory allocation and freeing simple for items or types that have the same lifetime. That's where I came across this, but I didn't really quite understand that. Memory padding alignment are two of the most important concepts in system programming because they directly affect performance and sometimes even correctness in certain CPUs. Let's use your struct as an example. So we have a float, char. What spelling is this? Is this from this? Anyhow, um, every data type has an alignment requirement. So on a 64-bit system, star is, I'm assuming, 1 byte. You mean? Okay. One's an 8-bit. Um, Maybe address refers to bytes and bits. Yes, this is much better. Acha. So what it's trying to say is the way your memory works is, again, if let's assuming the length of one word for your CPU is 1 byte, right? So you might think of it, your memory as is this box of lockers. Your 0th byte is over here. But you could assume in a sense that you have the 0th byte, then the first byte, second 0, 1, 2, 3, and then you have 4, right? So you have your 0th, first, second, third, and then you start like this. This is encompasses 4 bytes, right? And so if your entire data is within this, well, the CPU just has to fetch this entire block and into it, and then it's happy. But let's just assume if it does not start in these multiple, it starts somewhere over here and it goes for another one more, then you can see how your CPU has to fetch this and then has to fetch this only for this, which is, let's just say, extra work, right? 1 byte, so there's 6 of them now we used. Padding means there's nothing out here, just don't even worry about it. Okay.
alignment. And what you'll notice is that if you actually hover over this with your LSP server, it'll actually tell you something very interesting. It'll say the size 4 bytes and then alignment 4 bytes. What's that? Especially if I hover over this one, you'll see 1 byte plus 4 bytes padding, alignment 1 byte. So what is padding and what is alignment? Well, as it turns out, that's where this extra 12 bytes comes from. This is what that struct is going to look like in memory with all of the padding fields applied. So why bother with alignment and padding anyway? It's all to do with how fast the CPU can access that memory address. The compiler wants to place all of these elements at an address that is a multiple of the individual element size. So for example, that's why when we hover over this float term, we get an alignment 4 bytes because it's 4 bytes in size. However, if we hover over this one, you'll see alignment is 1 byte because each individual character in this array is 1 byte in size, and so the alignment stays at 1 byte. If we go to this pointer, you'll see we align at 8 bytes because the size of a pointer on a 64-bit system is 8 bytes. And so what we're doing here is once we get to this point in our struct with this U8 added, we're at 12 bytes. And you'll notice that 12 is not a multiple of 8. So what the compiler does is it pads by 4 bytes so that the starting address of this pointer is a multiple of 8. Now, over here at this boolean at the end, why do you pad 7 at the end to get us to 32 in total? We're up to 25 bytes here. Well, as it turns out, the alignment of a struct is based on the alignment of its largest alignment member, which in this case is a pointer, which is 8. And so what we want to do is get the total size of the struct to a multiple of 8. To do that, we pad by 7. Now I want you to pay attention to the default initialized values in this struct. We've got a 0 float, the characters high, -1, a 4, and a false boolean. Now what I've got down here is I've got a function that prints out raw bytes. So if you give it a byte buffer and a size, it'll just print out the individual bytes that make up that piece of memory. Now I've also got 2 pointers down here. I've got a struct pointer, which you can address the members of the struct as you usually would, as you can see here with the arrow key. I've also got a pointer to anything, which is just a byte buffer pointer that you can cast to anything. And you can see down here, I have casted the struct pointer to an array of bytes, which will simply be the size of the struct, like I was showing you before. And the point of this is I'm going to show you that not only can we print out the raw memory that makes up this struct and show you what I was showing you in the photo editor just before, but actually print it on the screen programmatically, but we can also change and modify the members of the struct with both this arrow method as you usually would, but also by individually changing the bytes of memory that make up the underlying data structure. So we're going to first compile this, and I'm going to show you the printout of the struct. Now, if you look through this printout of the struct, you'll notice that we have a 4 bytes for the float, which would be 0. We've got H and I, this is ASCII high.
Oh
And by
wow.
the way, if you're confused about the 10 here, this is to do with the representation of floats, which I'm not going to go into in this video.
It's
But for the
IEEE.
simple ones, you can see this is H in ASCII, this is I in ASCII. We've got a -1 here because it's a signed integer, and we've got a 4 here, which is the unsigned positive integer, and there's a 0 like for the rest of it, which would be our null pointer and our false boolean. Now, what I do here is I change a couple things with the arrow method. I set the negative to -39, I set the float to 3.14, and I flip the boolean to true. Now, if we print out those raw bytes again, you'll see we've got a very different boolean, Now, if we print out those bytes again, you can see we've got a very different floating point number. We've still got high, but our negative has changed to D9, which is the hex representation of -39. And our boolean over here has flipped
Wow.
to a true. So what we did there was we changed the struct as we usually would, and we saw a direct change in the actual array of bytes that underlies
Wow.
that data structure. We can also address the underlying bytes directly. So for example, if I go to my byte buffer pointer and I set the byte at index 4 to a G, what do you think is going to happen when I print the value of the string from my struct with the dot method, as you usually would access struct
Bonus struct.
methods? Well, what's going to happen when we compile and run this is that we actually get GI instead of high. So what you saw there was we literally just changed the underlying byte, and it had a change in how our struct member access, as we usually would with the programming language, actually represents that string to us. And we can do the exact same thing with the negative value, so I change it directly using the offset to 10, and you can actually see the offset if you hover over it in your LSP. It'll show you what the offset of that struct member is. So you can access it directly. And you can see here we get -44, which is 0xd4 converted to negative. Now the natural question arises, can we go in reverse? We have seen a high-level primitive like a struct be transformed into a byte buffer, but can we take a byte buffer and convert it into a higher-level primitive like a struct or like a data type? The answer is absolutely yes, we can. And once you understand this, you understand everything, like how file parsers work, how network protocols are structured, how file types work, how files are stored on disk. Like, it all just comes once you understand this, which is we can take an array of bytes, and provided it's in the right format, we can convert it into a high-level primitive like a struct
Oh
or a
wow.
data type
That'll be
or any
interesting.
other kind of representation you want, as long as that's defined. So what I've done here is I'm just setting our things we're dealing with to 0. So gMyStruct and gMyBuff. MyStruct is the struct we've been dealing with before. gMyBuff is just an array of uint8s, so an array of bytes. And what you can see me do here is I'm actually assigning the struct float to -9.29, and then I'm mem copying the 4 bytes, and you can see it's 4 bytes if you hover over the size of. I'm copying the 4 bytes that make up that float into this uint8 buffer. Now, what we're going to do next is pretty crazy, which is we actually cast the uint8 buffer to a float pointer, and then we dereference it and print it out with printf. You don't believe me that this is going to work? Well, let me show you. As you can see here, once we get to what's in my float buff after the mem copy, it is -9.29. So how the hell does that work? Well, as it turns out, once we do this mem copy, the 4 bytes that we see here that make up this floating point number, this is, before we changed it to 9.29, so this is not going to be what it actually is, but these get copied into our byte buffer. And then when we cast the byte buffer with no offset to a floating pointer, or any other pointer for that matter, it takes the first index of this, so like a 0, right? It'll take 0th a memory address, and it'll say to the compiler, okay, you can use this as a float. And then we dereference it. And you can see this in action in the very next example. I say, what are the first bytes of these? If you cast our float from our struct to a byte buffer, and you print out the 0th byte, and you print out the 0th byte of my buff, you can see that they are actually the exact same. So D7 and D7. And we can print out the raw bytes that represent that float like this. And so you can see. Now, as promised, I'm going to show you an example of the Linux kernel using this.
Okay, I'm gonna stop
This
it
is
over
the
here.
IP.
I'm a bit sleepy. Yeah, I think we'll cover this tomorrow. I think we were very too sleepy, but we did what we can. It's fun actually learning C. So C just keeps on impressing me. I don't know how, but yeah, that was fun. So thank you for tuning in for another late night session with one and only, and we'll keep up tomorrow with our NeetCode/NeetCode grind and our fast API using Redis. So see you.